Hello, I will present our paper titled Excessive Transverse Coordinates for Orbital Stabilization of Underacted Mechanical Systems. So in a single sentence, we show how one can use so-called excessive transverse coordinates to design exponentially orbitally stabilizing feedback for periodic motions of mechanical systems, with a special emphasis on underactuated mechanical systems. So a bit more detailed problem formulation. So we consider underactuated all-Lagrange systems written on the following form. Here Q are the generalized coordinates with nq degrees of freedom, q dot the generalized velocities, u are our control inputs, and we say that the system is underactuated if we have less control inputs than we have degrees of freedom. Now, to keep things simple in this talk, we will consider the system written on regular state-space form, given here as a dynamic control affine system, with x denoting the states of the system, given as the generalized coordinates under this, and we will denote by n twice the degrees of freedom. So with this in mind, the task we consider in the paper is the following. Given a T periodic solution, here denoted by capital T, denoted by the star subscript as shown here, and with a known nominal control input U star, the task is to find an exponentially stabilizing, orbitally stabilizing controller, given here as a mapping K, which is completely state dependent, and such that the corresponding closed loop system admits this desired periodic solution Q star as an exponentially stable limit cycle, at least locally. So for those not familiar with orbital stabilization, let us remind ourselves of the notion of actual orbital stability, or often called Poincare stability. So given a known solution x star of an autonomous closed loop system on Rn, and if we denote by eta star the corresponding orbit, that is the set of all states along this normal solution, then we say that this solution x star is exponentially orbitally stable if we start sufficiently close to the trajectory, that is, this infimum distance is satisfied, then we will exponentially converge to it, that is, this infimum distance will exponentially decay towards zero with rate c2 and overshoot c1. Now, the idea we use in the paper to ensure this is by using reparameterizations and a so-called projection operator. That is, we assume we know some reparameterization of the normal orbit, denoted here by x of s, in which s is a monotonically increasing scalar variable, which can be seen as a reparameterization of time, and which the reparameterized trajectory naturally satisfies this equality. Together with this reparameterization, we assume that we know a projection operator for this reparameterized trajectory. That is, this is some mapping which in a neighborhood of the normal trajectory maps each state to a corresponding point upon this normal trajectory. That is, it recovers the parameterizing variable s. Necessarily, it has to be a left inverse of the normal trajectory. Now, if for a fixed point s hat along this orbit, if we consider the set lambda of s hat, which here lambda is defined as follows, as every state in the neighborhood of the normal trajectory which maps to a particular s through this projection operator. Now, this set will trace out some hypersurface which locally is transverse to the flow of the normal trajectory. This surface is often referred to as a moving Poincare section. And the idea in order to destabilize or design orbitally stabilizing feedback is the following. Suppose we can find a set of coordinates which evolves and spans this section. And if by control action we can enforce strict contraction of these coordinates towards their origin, which corresponds to the normal orbit, at all points along the orbit is closed, then necessarily this strict contraction corresponds to asymptotic stability. Now, in order to do this, we of course have to know a set of coordinates which then spans these sections, often referred to as a set of transverse coordinates, as they then evolve transverse to the flow of the trajectory. While such a set of coordinates will always exist, so n- independent coordinates will always exist for a periodic trajectory, finding them is not necessarily trivial always. So what we show in this paper is that you instead can consider an excessive number of coordinates. That is a generic set of excessive coordinates whose number equals n, but necessarily, as the name implies, they only contain a set of n minus 1 with one excessive variable at all times. Now these variables have a very easy definition. Simply, for a given x, they are the distance from the x to the corresponding point on the orbit, so the reparameterized orbit, in which the parameterizing variable s is found through this projection operator. And we denote by them by xperp. Now necessarily, if we change the projection, we will also change these excessive transverse coordinates. But nevertheless, they have the same interpretation as some distance measure from the given state in the neighborhood of the orbit to the corresponding orbit. Let's look briefly at some local properties of these coordinates by defining the Jacobian matrices omega and gamma as shown here, which are just corresponds to the Jacobians of the excessive transverse coordinates and to the projection operator evaluated along the trajectory. Now this means that for a small change in the states of the system about the normal trajectory, they are mapped to small changes in the excessive coordinates and in the parameterizing variable s through the matrices omega and gamma. Now it's easy to show that this matrix omega is a projection matrix. Its square is equal to itself. Its left annihilator is the Jacobian gamma, while its right annihilator is the flow of the vector field. That is x prime, with x prime denoting the derivative of the normal trajectory. Now from this we can deduce the following. This projection matrix omega maps just these small variations of the transverse states back into the plane on which they evolve, which necessarily must correspond to the tangent plane of the moving Poincare section evaluated at the orbit. Likewise, this implies that these transverse coordinates, the plane they evolve upon, it is orthogonal to the gradient projection operator. So this inner product with its Jacobian vanishes. Now this transversality condition is therefore important and also shows that these are indeed an excessive set of coordinates, as we have to ensure that this constraint is always satisfied, this transversality constraint. Now in order to ensure stability of the origin of these coordinates, which necessarily must correspond to the normal trajectory we want to stabilize, we will want to perform a so-called transverse linearization in order to find the linearization of the dynamics of these coordinates. And if we can stabilize the corresponding system, then we stabilize the normal trajectory orbitally. So we show in the paper how to do this for a mechanical system. Here we just represent the same linearization for the control alpha and dynamical system as we saw before. So the transverse linearization results in the so-called linearized transverse dynamics, so the linearization of the dynamics of these excessive coordinates, which are a linear periodic system of the following form, but which is subject to this transversality condition as we saw earlier. In fact, this condition is quite important, as without it, this system can never be stabilizable. That is, even regardless of what the control input V is, it will always have a solution in the direction of the flow of the normal solution. Hence, we have to include this transversality condition in the linearized transverse dynamics. So in order then to stabilize this system, the main result of this paper is then to show how to do this by including this transversality condition. So this leads us to the main result of our paper, which is simply the following. If one can find a symmetric positive definite matrix function R_perp, which satisfies the following matrix equation for all points S along the solution, where pi and q are some symmetric positive definite matrices and kappa is some positive scalar number, then this LQR-like feedback with S found through the projection operator will render the normal solution exponentially orbitally stable, at least locally. So quickly having a look at this equation, what's inside the brackets here is nothing more than a periodic differential Riccati equation. But as mentioned on the previous slide, solutions to the system can only be stable, possibly stable, on solutions which satisfy the transversality conditions. That is, the pair A perp and B perp cannot be stabilizable on their own, so what's inside the brackets here can never be equal to 0. So in order to include the transversality constraint, we can just multiply from the left by the transpose of omega and from the right by omega itself. And then if the system is stabilizable on these sets of solutions, then this matrix equation can possibly have a solution, and its solution leads us to this LQR feedback. Now, there are other ways of arriving at such solutions as well. So in another paper, we show that you can use a so-called comparison system, and there is also possible of stating different linear matrix inequalities as well. But in the paper, we consider the following. So let's show in an example that this scheme actually works. So we'll consider the well-known cart pendulum system with the task of generating oscillations about its upright equilibrium. So this system corresponds of a cart driven along the horizontal by some external force U and is position denoted by R. Attached to it is an unactuated pendulum whose angle is theta, and we will consider the task of generating oscillations about the unstable upright equilibrium. For simplicity, we consider just unit masses and the pendulum point mass, such that its equation of motion have this simple form, with the second equation unactuated as seen here. In order to generate a desired solution, we consider the following approach based on virtual constraints. That is, we assume that along a normal solution, each of the generalized coordinates can be written as a set of basis functions. So for instance, some polynomials, phi of r and phi of theta, parameterized by our parameterizing variable s, which is strictly monotonically increasing along the solution. That is, its nominal velocity can be written as some function rho of s itself. Now, if we assume the invariance of this from the second unactuated equation, this reduces down to this following first order differential equation in rho, having to be satisfied at all points along the trajectory. Now, if for a choice of these functions, we can find a solution of rho which is positive for all points connecting the endpoints of the normal trajectory for a choice of s, then this is a solution, a very feasible solution of the mechanical system. So as an example, we took phi r and phi theta as shown here, so some trigonometric polynomials in which s simply goes from 0 to 2 pi. Now, with the choice of constants shown here, the found solution for rho is shown here as the unique positive solution bridging 0 and 2 pi. But since the system is mechanical, we of course also have a corresponding negative solution. Now, in order to stabilize this, before solving the matrix equation, we need to know the projection operator. So for this, given our assumption on the evolution of theta, that is, that it should satisfy this relation, we can find our projection operator P as the root of this implicit equation in terms of S. Likewise, we can find its Jacobian as well, just using the implicit functions theorem. With this, we solved the matrix equation, and to show that it works, we have here a simulation. So starting from a slightly perturbed initial conditions, we converge to oscillating about the 0 position with upright equilibrium. With the second here, we see that the control input, the nominal control input, is the given dotted red line, and the actual is the blue one, which converges after about 8 seconds. And in the paper, we show that it also can handle a little bit of noise as well. Okay, so let me end with some final remarks. So we have shown that we can stabilize orbitally the system using these excessive transverse coordinates by using a transverse linearization and the so-called stabilizing the linearized transverse dynamics by solving a matrix equation. Now, this scheme is a stepping stone to, for instance, robust orbital stabilization as well, and it can also be used for certain non-periodic motions. So if you look briefly at this figure shown here, if we can ensure contraction between two equilibrium states of the system, for instance, corresponding to swinging up this cart pendulum, then we can actually ensure that we can have a single control scheme which stabilizes this swing up motion and stabilization at the equilibrium point without having to switch between swing up and stabilizing. That was all I had time for. Thank you.